Hello BC Calculus students, this is Mr. Johnson and this is section 2.4 which is on continuity. So the first thing we're going to do is just review the three different requirements for continuity, and in AB what you learned was that at a value A the function must exist first. So we test that there's actually a function value at a particular x value. The second one is that we test that the limit as x approaches A of that function exists as well. Now, the limit by itself does not necessarily guarantee that there's a function value there, because the limit is really looking at the area around that x value. But to make sure that a limit exists, we have to make sure that the limit as we approach the value from the left of the function is equal to the limit as we approach the value from the right of the function. And again, the reason that these two items are really important is because if you take a look at a graph, let's say that you have something that looks something like this, okay, and you have a hole in the graph and then maybe a point right here at A. The reason that it's important that we look at these separately first, but then together, is because in this particular situation, you can see that this graph would be discontinuous at A. While the function exists up at the top here, and while the limit exists from the left and the right, the two are not the same, and therefore it's discontinuous. So the last part of continuity is that we have to have an agreement. So the function must equal the limiting value as x approaches A of f of x. So again, make sure you pay attention to the notation here, but also pay attention to the fact that we look at these three items, and the third one is really all of it combined, but we can't just look at pieces because then it might be really misleading to us. All right, in terms of finding points of discontinuity, we're going to look at um, specifically the denominator of the function. So if we have some sort of function where we have a rational function and there's a denominator, um, when the denominator is 0, then we have a situation where we have a discontinuity of some sort. Another situation where we may have a point of discontinuity is when the function is defined that way. So for instance, as an example, if we were to take like the greatest integer function, which I'll talk about in a minute, the greatest integer function by definition takes a value and it is either an integer to start with or it rounds down to the closest integer. So for instance, 0 is 0, but anything up to the number 1 is also 0, except when you get to number 1, then it is 1 because 1 is an integer, and anything up to 2 is going to be down to 1, which is the lowest or closest integer, and then when you get up to 2, then it becomes 2, which is an integer, and so on. So what you have is this sort of step function, this discontinuity that's built into the definition of the function itself. So points of discontinuity in general, we're going to look for something in the denominator that's an issue of some sort. But then just by definition, we may have these functions that are either piecewise functions or just maybe a function like the greatest integer function, where by definition there are discontinuities built into it. Okay, I'm going to walk you through example 1, which is going to build the three parts of um, the continuity checklist. So for the first one, we can see that there is a denominator, and so that's where we're going to focus our attention when it comes to discontinuities. So we say that in this case that it's we're looking for which of the following functions are discontinuous. So the discontinuity occurs when x is equal to 2, because that's what makes the denominator 0. And if we were to look at our checklist, which of the three items shows that it's not continuous? Well, the very first one, f of 2, does not exist, and therefore we have, check number 1 on our list does not work, and therefore we don't have to even worry about continuing on the rest of them. So we could certainly test the limit, but it doesn't matter. As soon as one of those three items on your checklist doesn't work, then we're done with our continuity checklist. For part B, we have in the first part 1 over x squared. So we have another situation where we have this denominator, and of course, if x is 0, it would cause a discontinuity. So then in our checklist, which of the three would fail. Well, number one, we have f of 0, and that is 1. So this does exist. So then we would move on to the second one. We take a look at the limit as x approaches 0. Now remember, when you look at a limit, you don't really worry too much about x equal to 0. We want to look at around 0. So instead of using the information right here where the function's 1 when x is 0, we would focus our attention on when x is not 0. So what's happening around 0. And in this case, we have that situation I had talked about in our last section where you have 1 or a number divided by 0, and that limit then would not exist. Okay, for part C, we have another fraction. It's actually the same as part A. So we have a discontinuity when x is equal to 2, because that first part in our piecewise function would fail in the denominator equal to 0. We have a function value at x is 2 equal to 1, so that exists. Then we have a limit as x approaches 2, which is going to focus on x squared minus 2, or excuse me, minus x minus 2 divided by x minus 2. And we could factor this. So we get x minus 2 and x plus 1 and then x minus 2 in the denominator. The denominator here would cancel with the factor in the numerator, leaving us just with the limit as x goes to 2 of x plus 1, which if we evaluate by substitution is 3. So does the limit exist? Yes, the limit exists as well. All right, but we know there's discontinuity here, at least we're checking for that. So when we compare the two of these, f of 2 is not equal to the limit as x approaches 2 of f of x, and therefore it's discontinuous at x is equal to 2. Okay, so if you look at parts A, B, and C, these are the three different situations in which the three parts of continuity would fail to exist. Okay, with part D, we have the greatest integer function. So let me just draw that out for you again. So what happens is that you take any particular number and you either keep it at an integer if it is an integer, or you round down to the closest integer. So if we were to just put a little scale on here quickly, let's say each of these tick marks here is 1. So 0 is going to be 0, and everything up to 1 is 0. And then from 1 all the way up to 2 is 1. From 2 all the way up to 3 is 2. 3 all the way up to 4 is 3, and so on. So when we're looking at this and the question is, where is it discontinuous? We would say at every integer. Let's just call the integer a so we can write down what's going on. So first question is, does f of a exist? And the answer is yes. We can see from our graph that every one of these little closed circles here is representing that the function exists at every single one of the integers. So for instance, f of 2 is equal to 2, f of 1 is equal to 1, and so on. However, if we look at the limit as x approaches a of f of x, it does not exist. And we can see that as we analyze each of these integers, that the limit from the right of 1, for instance, is 1, but the limit from the left of 1 is 0. And so the two-sided limit does not exist, and therefore it's discontinuous at every one of the integers. All right, we're going to move on to the next page. Okay, in this example, we're going to look at a piecewise function, and we're going to check for what value of k, based on this function, allows f to be continuous when x is 2. So the first step is to look at f of 2, and in our piecewise function we get k. So that doesn't really help us necessarily, but that's just a statement in terms of our checklist. That's number 1. Number 2 is going to be the limit as x approaches 2, which we're going to use the first part of this piecewise function. And in this case, similar to the examples on the last page, we can cancel the x minus 2. So we get the limit as x goes to 2 of the quantity 2x plus 1. That gives us 5. So we have our function value equal to k, our limit as x approaches 2 of the function equal to 5. For it to be continuous, we have to make sure that the function value is equal to the limit value. And since the limit value is equal to 5 and the function value is equal to k, then we know that k must equal 5 in order for f to be continuous. All right, let's talk about left and right continuity. So a function is continuous or considered continuous from the right side at a number a if the limit as x approaches a from the right of the function is equal to the function value at a. So for instance, if you had, I'll just draw sort of a simple example here. Let's say that you had some graph that looked like this and maybe like this, okay? And let's say that's a. This particular function would be continuous from the right side of a, or right continuous, because the limit as you approach a from the right side is equal to the function value at a. If you have a function that is left continuous or continuous from the left side, then you have limit as x goes to a from the left of f of x equal to f of a. So you can see, kind of a similar drawing here, I guess. If you had, let's say, a function that looks like this and like that, at a, it's continuous from the left side because the limit from the left is equal to the function value at a. Okay, what about the greatest integer function? So if we just quickly plot this again. So we have sort of these steps here. Okay, is this right or left continuous? Well, if we take, for example, this is 2, and that's 1 and 2. So if we were to look at 2, and we look at from the left side of 2, the limit is 1. The function value, however, is 2. So that doesn't work very well. I'm going to write that down so you have it. So we have the limit as we approach 2 from the left of f of x is equal to 1. Again, we have f of 2 is equal to 2. And we have the limit as x goes to 2 from the right side of f of x is 2. So because these two are equivalent, then this would be considered continuous from the right side. Okay, let's move on to the next page. Here we're just going to organize some general ideas when it comes to continuity, what types of properties exist and what types of functions are continuous. So the first thing is a little theorem we have in our textbook. It says that if f and g are continuous at a and c, and c is a constant, then the following functions are also continuous at a. So we can add these two functions and they still are continuous. We can also subtract them, they're still continuous. We can multiply either one of them by a constant c and it still is continuous. We can multiply them and they're still continuous. And then last, we can divide them. However, we have to make sure that, for instance, that denominator we have evaluated at a is not going to create it to be equal to 0. So that's the only restriction on that last one. But we can do a lot of mathematics behind continuous functions and still get a continuous function out of it. There's a theorem in our book that comes next that talks about how a polynomial is continuous everywhere. That entire idea is that on the domain negative infinity to infinity, polynomials are continuous. And then a rational function is continuous everywhere that is defined. And that's sort of what in that fifth spot here I was talking about, is that a rational function is going to be continuous as long as it is defined there. And that's really all about the denominator. Okay, types of functions that are continuous everywhere on their domains. So we have polynomials. We have rational functions. We have root functions, trig functions, exponential functions, logarithmic functions, and then the other one that's sort of just the extra one that ends up coming up a lot but doesn't really fit in a specific name is the absolute value function. Okay, so just keep in mind that the majority of the ones that we deal with in the context of these definitions, these are all continuous functions. Now, what is real common on the AP exam is that they'll put in a piecewise function. So that's kind of stuff that we have to be concerned with when it comes to continuity, and then ultimately differentiability. Here's a couple theorems, just two quick theorems, one on this page, one on the next, that talk about compositions of functions. This one I'll give you an example in just a moment, but if f is continuous at b, and you have a limit as x approaches a value a of a different function g of x, and it's equal to b, so again, f is continuous at b, the limit of a particular function as you approach a value is equal to b, then the limit as x goes to a of the composition of these functions is simply f of b. Here's really the equation that this is talking about. It's right here in the second part. So if you were to take the limit as x goes to a of the composition, as long as f is continuous at b, you can sort of pass this limit operator through to the inside and evaluate and take the function of that. And again, I'll show you that in a moment. Let's go to the next page. One last little theorem here, and then I'll give you an example of what I was just discussing with you. So if f is continuous at a, and f is, excuse me, I think I misspoke. If g is continuous at a, and f is continuous at g of a, then the composition, which is f of g of x, is continuous at a. Both of these theorems, if you really dig into them, are pretty intuitive, but here's an example from an older exam. I don't really remember which year, but it says the graph of f is shown in the figure below. The value of the limit as x goes to 1 of sine of f of x is what? And this is a calculated problem. Now, sine of x, y equals sine of x, is continuous everywhere on its domain, which is everything. We saw that in the list. That was one of our trig function, the list there. So sine of x is continuous. And so what we can do then is we can take the limit operator and sort of pass it through to f of x. And if we look at our graph of f that's shown there, the limit as we approach 1 is 2. So what we have here is now sine of 2. And if you use your calculator, you're going to get option A. Okay, a couple more things in our section here. One is the intermediate value theorem, which we've talked about in AB a lot, of course. You all should know this, but it says that we're looking at a function and it's continuous on an interval a to b, and that interval is closed. And let n be a number that is in between f of a and f of b. And the theorem says there must exist a number c on the open interval a to b such that f of c is equal to n. Okay, what this means really is, and again, sometimes the theorems can be a bit abstract in how they're worded. The idea behind it is that if you have some function that, let's say, goes from here up to here, and we know it goes from a to b and it's continuous, it must cross every y value in between. So for instance, just as a simple example, let's say that this is -2 and this is 10. Well, this particular function, it's guaranteed that it has to cross 4 because 4 is in between -2 and 10. It has to cross -1 because -1 is in between -2 and 10. It has to cross 9 because 9 is in between -2 and 10. It doesn't have to cross 20. It might, we don't know, but it's not a guarantee. What's guaranteed if it's continuous on this interval is that it crosses every y value in between. It has to just logically, because how can you go from this point to this point without crossing all of those values, and if it's continuous, which we're told it is. So that's the intermediate value theorem. Here's one example of that. Sometimes it's used for x-intercepts. So in this case, it says show that there's a root of the particular equation between 1 and 2. So we're looking for proof that there's an x-intercept, and I'm just going to name this function f of x. So we're going to look at each of the points. So we're going to look at f of 1 and plug that in. So we have, let's see here, we plug in 1. So we get, let's see, that gives us -1. And if we plug in 2, that's going to give us 12. Okay, so what we know is that this particular function, and maybe we should draw this out really quickly because it will be a little different than the way I drew this example over here. So if we have when x is 1, we have the point -1, and this is not really going to be the scale, so bear with me. So we have 1, -1, and then we have 2 and 12, which is maybe like this. And we're told that these two connect, okay? We don't know how they look. All we know is that it's continuous from 1 to 2. Well, as you can see, I had to cross the x-axis. It was something that must have happened just intuitively. So how do I communicate that? Well, one of the things that we can say is that we can use compound inequalities, which is helpful. So we could say since f of 1, which is -1, is less than or equal to 0, which is less than or equal to f of 2, which was 12, there exists a number c in the interval a to b, which is what they asked us to look at, such that f of c is equal to 0. So that's the idea behind the intermediate value theorem, is that we're looking at really what's happening on the endpoints of that interval, and then we're guaranteeing that everything in between those endpoints is crossed along the way if it's a continuous function. Okay, our last example says let f be a continuous function on the interval -3 to 6, and f of -3 is equal to -1, and f of 6 is equal to 3. Then the intermediate value theorem guarantees that. All right, I do like to sketch a picture if it's helpful. So what we have is the point -3, -1. This won't be to scale either, but gives us an idea of what's going on. And then 6, 3. So let's say that's there. Okay, and then these two connect somehow. We don't really know. We know it's continuous. Okay, so the first part A is f of 0 is 0. Well, my picture, who knows if that's right, but I did not go through 0, 0, and I didn't have to. 0, 0 is way too specific. It certainly could be the case that it's going to go through 0, 0, but it's not a guarantee. Okay, f prime of c is equal to 4/9. Now I'm just curious, if we were to find the slope, so 3 minus -1 divided by 6 minus -3, we sure do get 4/9, don't we? Now, that's sort of a true statement. However, this is the mean value theorem, not the intermediate value theorem. So be careful. That is a true statement, but it's not what the intermediate value theorem guarantees. It's what the mean value theorem guarantees. Part C, in between -1 and 3, x is sort of contained. Well, I guess the way I drew it, it is. But I mean, what if as you connected these points, you went way up here like this? I don't know, or something like this. I mean, the way I drew it, we're between -1 and 3, but we could kind of go really crazy in between as long as these are connected and it stays as a function. So no, there's not a guarantee here that we're between -1 and 3. Let's skip D for a minute. So part E says f of C is equal to 0 for at least one value in between 1 and 3. The problem is that -1 and 3 are y values, and we're not concerned with the y values for C, because as you can see, based on the problem, x is equal to C, not y. These values here are y values that I think they're trying to distract us by. We need to look for the x values. So we're looking for option D. Option D says that the function's equal to 1 for at least one value in between -3 and 6. And that absolutely is true because all values between -1 and 3 are going to be crossed, and 1 is part of that. And we know that the x values are contained by -3 and 6. Okay, now you can try some of these on your own for 2.4, but that's it for us in this lesson. Thank you.